In this video, we're going to talk about theoretical probability. So we are going to look at what the sample space is for a given situation, how to compute our probability, and also use combinations to describe our situation. So a few definitions here. Sample space represents all the different equally likely outcomes. So we're going to look at the set of everything that could happen in these given situations. An event is the subset of all the outcomes that meets a given condition. So there's different events that could happen within a sample space. And then probability basically boils down to the ratio of the number of outcomes for a specific event divided by the total number of outcomes in our sample space. So some notation that you may see with probability. The probability of some event E, we use capital P to represent probability, and whatever's inside the parentheses represents a certain event or outcome. And so that ratio for the probability of any specific event is the number of times that event occurs or could possibly come out, and the number of outcomes in our sample space. So this is our total. So first example, we're going to look at some spinners here. So list the sample space of outcomes when spinning both spinners. So with spinner A, we've got 4 options, 1, 2, 3, and 4. For spinner B, we've got 3 options. So I'm going to write out all of our different outcomes for that. So I ended up with 12 different outcomes. If I list the number from spinner A first, I could get a 1 and then a 1 from spinner B. I could get a 1 and 2 and a 1 and 3. I could get 2 and 1, 2 and 2, 2 and 3, etc. So I've got 12 different outcomes here when I spin both spinners. So we want to find the probability that we are going to get the same number on both spinners. Now, as I look at the probability here, recall that we talked about the sample space being the set of all equally likely outcomes. So in our spinner example, we are equally likely to get any of these 4 numbers in spinner A and equally likely to get any of these 3 numbers in spinner B. So all of these outcomes are equally likely to happen. So that doesn't affect anything that we do with our probability down below. So first one, what's the probability that we get the same number on both spinners? Well, I take a look at my sample space, and I've got 1 and 1, 2 and 2, 3 and 3. And there's no 4 and 4 because there's no 4 on spinner B. So I have a total of 3 different ways that my event can occur. And I have a total of 12 outcomes in my sample space. So I could simplify that to 1 over 4. That would give me a decimal of 0.25 or 25%. Our second example, what's the probability that we have a sum of numbers that equals 4? So I'm going to go back here. I could spin a 1 and 3, 2 and 2, or 3 and 1. So again, we've got 3 different ways that our event can occur. We have 12 total outcomes in our sample space. So same answer as before, 25%. Our last example here, what is the probability that spinner A is going to be greater than spinner B? Let me go back to my sample space. Get rid of this here. Well, I'm looking for spinner A, which I put on the left side, to be greater than spinner B. It's not going to work for this first column here. Second column, 2 is greater than 1, so I could include that one. 3 is greater than 1 and 2, and then all 3 of these. Spinner A is greater than spinner B. So that's a total of 6, and I still have 12 in my sample space. So that's 1/2 or 50%. Okay, next example, rolling a die. So what is the sample space for rolling a die? So it's just one dice, 6 sides, and we could have 1, 2, 3, 4, 5, 6. So find the following. What's the probability of rolling an odd number? And what's the probability of rolling a number greater than 4? Once you quick pause, try to set that up yourself. So our first example, odd number, that's 1, 3, or 5. So there's 3 possibilities there. Total of 6 outcomes in our sample space. So 1 over 2 or 50%. Now rolling a number greater than 4, go back to my sample space. Because it's such a small sample space, this is not one that we need to likely look at our sample space as often as some other examples, but just to double check, I see that we've got just 2 numbers there, greater than 4. So that's 2 out of 6, or 1/3. Usually I do 1 decimal, so 33.3%. So now in this example, we're looking at how large the sample space is for rolling a die 2 times and the probability of specific events here. So now if we've got 2 die that we're rolling, we've got 6 options for our first roll, 6 for our second. So we take 6 times 6, that gives us a total of 36 different options here for different outcomes in our sample space. So our first example, probability of rolling an even number followed by rolling a 1. Now looking at this, we see that it's very specific that it has to be an even number in our first roll and then a 1 in our second roll. So be careful when you're looking at the event that's being described, how specific you need to be in determining how many outcomes you could have there. So if it's an even number first, it has to be a 2, 4, or a 6, and then with our second roll, we have to have a 1. So that narrows it down to just 3 outcomes there out of 36, which is 1 out of 12, or 8.3%. Probability of rolling an even number and a 1. Now that's not telling us that we need the even number first. So these 3 still count for this second event, but we could have the 1 first followed by the even number. So if we just flip those numbers around, now we double how many times we can get this event. So that's 6 out of 36, or 16.6 repeating, or 16.7%. Last one, probability of rolling a sum that is less than 6. So my sample space here does not show sum. You can Google search for a sample space that shows you the sum, but I see this is 2 here, this is 3, and I can just keep going, but I want anything less than 6. Well, I'm almost done, so I'll just keep going here. Anything more than that, I'll get 6, so my cutoff is kind of right there. And you see that we've got this diagonal pattern there for the sum, but I count up 10 different ways that we can get a sum less than 6. Divide that by 36, and we've got 27.7 repeating, or 27.8. So our last set of examples, we're going to be looking at a deck of cards. So just standard deck, we've got 52 cards. There are 4 different suits, 13 cards in each suit. So it starts with an ace, and then the numbers 2 through 10. And then we've got 3 face cards, jack, queen, and king. So our first example is probability of drawing a club. I just want to make sure that I'm looking at the whole picture. I know that there are 52 cards here, and I have 13 cards in each suit. So that means there are 13 clubs. I also know that each suit represents a fourth of the deck, so 13 over 52 simplifies to 1 over 4, which is 25%. Our second example, drawing a 10. Well, there's a 10 for each suit, and there are 4 different suits. So that's 4 out of 52, which is going to give me 7.7%. My last example is drawing a red face card. So I'm just going to go back up to my sample space and double check. I know that there are 3 face cards for each suit, Jack, Queen, and King, and there are 2 different suits that are red. So that gives me a total of 6 events, or 6 outcomes to get this event. So 6 out of 52, which is about 11.5%. Okay, last set of examples here. If we're randomly drawing 3 cards, we've got a few different situations. The first one being we are drawing 3 different hearts. Now, all of our other examples was just drawing 1 card, rolling 1 die, or if there were 2 different events happening, it was a combination. So what's the sum of 2 dice, or what's the combination of spinning 2 spinners? So here, probability of drawing 3 hearts, I need to look at what's the probability of drawing 1 heart for my first card, what's the probability of drawing a heart for my second card, and for my third card, because it's going to be different. I'm not picking a heart, putting it back in. I'm drawing 3 different cards, and I want all 3 of them to be hearts. So I need to look at my first card. There are 13 different ways I can get a heart when I draw my first card. Now, I've picked that card, it's out of the deck, and I need to grab a second card. I need that to also be a heart. So my first card being a heart, I now only have 12 hearts left in my deck, and I only have 51 cards to choose from. So now that the probability of grabbing a second heart changes. Same thing with my third. So I end up with this ratio here, because I have to multiply the probability for each heart, and so that's 1.29%, so pretty low. Next example is drawing 3 jacks, and it's similar, but it's going to be much lower because there are far less jacks than there are hearts. So now I only have 4 jacks in my deck. So I start out with my first card being 4 out of 52. Once I grab a jack, my second one, now there's only 3 jacks left out of 51 cards to choose from. And my third card, 2 out of 50. That ends up with a really, really small percent chance that we're going to grab 3 jacks. Okay. And then looking at one more example, drawing 3 different numbers. Now in this case, we'll just call ace. I know that ace has a value of 1 in a lot of card games, but ace isn't a number, so we'll just say 2 through 10. All right, so if we got the numbers 2 through 10, that means there are 9 different cards that have a number on it for each suit. So 9 cards times 4 suits is going to give me 36 total ways that I can draw a card with a number. And so that first one is going to be 36 out of 52. Now if I've already drawn a number, now there's 35 left out of 51, 34 out of 50. And that's going to give us a much better chance of drawing 3 numbers as opposed to the other 2 examples, because there's so many more to choose from.